In this module, we'll treat blockchain as a trust layer that plugs cleanly into existing systems rather than replacing them. You'll see patterns for connecting ledgers with ERPs, case management tools, message buses, APIs, and monitoring stacks in real enterprise and government environments. Most enterprise and government landscapes look like this: multiple systems of record, each authoritative in its own domain, but effectively islands. Finance, logistics, HR, and citizen records all maintain their own truth, schemas, and governance processes. To make the business work, we stitch them together with custom integrations. Over time, those links turn into a fragile mesh, hard to document, harder to change, and risky to touch. All of this sits under strict compliance, zero downtime expectations, and long approval cycles. So even when everyone agrees change is needed, the underlying trust fabric is extremely resistant to evolution. In that context, blockchain is not a rip and replace move. It becomes a shared trust layer that sits beside your existing ERP, CRM, logistics, and HR systems. Those systems remain the systems of record for sensitive data and internal workflows. Middleware decouples them from the ledger so you can evolve the chain without breaking legacy apps. The ledger's role is to manage cross-party integrity, agreements, proofs, and shared events. This approach respects strict governance and zero downtime requirements while still enabling gradual, low-risk modernization. APIs and events act as the nervous system connecting legacy systems to the blockchain rail. Synchronous APIs handle intent: submit this transaction, or give me the latest state. They provide controlled entry points with validation, authorization, and policy checks. Event streams then carry everything that happens after. When something changes on-chain or off-chain, you publish an event to Kafka or your message bus so downstream systems can react. To keep reads fast, apply CQRS. Treat the chain as the right authority, then project that state into local query-optimized databases for reporting and user interfaces. Enterprise systems usually operate much faster than the blockchain consensus layer. If you try to keep them perfectly in sync, consensus latency will either throttle your core systems or tempt teams to bypass the ledger. Instead, treat the ledger as a slightly delayed but authoritative source of truth. Applications accept that local state is provisional, then reconcile when blocks are finalized. Architecturally, that means asynchronous flows, idempotent operations, durable queues, and message replay. So you can safely reapply events after confirmation and heal temporary inconsistencies without manual repair. Here, the key idea is data minimization as the bridge between line-of-business systems and a permissioned ledger. Your SAP, Oracle, CRM, or document systems continue to hold full records, including PII and regulated fields. Before anything touches the blockchain, a filter membrane extracts only what's necessary for integrity, typically hashes, timestamps, and selective metadata. Those minimal proofs are anchored on-chain, giving you strong auditability and non-repudiation, while sensitive content stays off-chain under your existing GDPR and privacy controls. So trust is shared, but privacy and regulatory scope remain tightly contained. Oracles form the bridge between blockchain and the real world. Smart contracts can't directly call web APIs, read market feeds, or talk to IoT sensors. An oracle watches those external sources, validates what it sees, and then injects a signed fact into a transaction. In a regulated setting, the key question is, who runs the oracle and how is it governed? You're effectively reintroducing a trust anchor. That means you need controls, redundancy, attestation, audit logs, and fallback procedures when Oracle data is delayed, missing, or disputed. Once you connect blockchains to external systems, the Oracle layer becomes its own trust infrastructure. Treat every external feed as untrusted until it passes through a validation funnel. Start with redundancy. Multiple independent sources for the same fact, so you can compare, vote, and isolate faulty or malicious feeds. Then apply validation logic, sanity checks, threshold rules, anomaly detection, and potentially reputation scores for each source. Finally, ensure full auditability. Persist raw inputs, decisions, and signatures so investigators can later reconstruct exactly why the chain trusted a given piece of data. Introducing oracles and their supporting infrastructure also requires clear operational models, not just technology. First, governance. Which organization runs each node, and who is accountable when something breaks or needs upgrading? Second, SLAs. You must codify latency, uptime, and support expectations so downstream systems can rely on them. Third, IAM. Operators need strong authentication and access control, aligned with enterprise security standards. For a blockchain-based trust platform, observability is non-negotiable. You need continuous insight into transaction throughput, node health, and peer behavior to spot issues before they become incidents. Monitoring and logging turn the ledger from a black box into an auditable operational system. By exporting metrics into tools like Prometheus and visualizing them in existing dashboards, enterprise and government ops teams can apply their standard monitoring and incident response practices. Treat your blockchain network as just another critical application your SOC monitors. Key blockchain signals should flow into your SIM in real time. Watch for consensus anomalies. Unexpected forks, validator flapping, or rising latency can indicate misconfiguration, failure, or active attack. Track key management events, certificate issuance, rotation, and failed access attempts all need correlation with IAM and HSM logs. And monitor abnormal smart contract activity. Sudden spikes in specific methods or addresses can reveal exploitation or fraud before business users notice. For blockchain-based trust infrastructure, DevSecOps is how you keep the ledger and smart contracts trustworthy over time. Think of the pipeline as a loop. Code moves through automated tests, then policy checks, then security scans before it's ever deployed. Automated testing includes static analysis and dependency scanning tuned for chain code and node components. Policy as code encodes compliance rules as executable checks, so legal and security requirements become gates, not slide decks. Finally, use gated promotion, dev, to test to staging to production, so only audited, compliant builds reach consortium participants. In regulated environments, you can't treat blockchain upgrades as ad hoc DevOps tasks. Every protocol, configuration, or smart contract change has to align with your existing change management process, typically via a change approval board. Governance then operates on two layers: off-chain decision-making and on-chain enforcement of what's allowed. Together, they create a strong audit trail, so every change is reviewable, attributable, and legally defensible. This blueprint pulls together everything we've covered into a single operating model. At the bottom, your existing systems of record stay authoritative, but they expose events and APIs through an integration layer. That middleware handles translation, routing, and buffering, so the ledger never becomes a brittle point of coupling. Above that, the blockchain core and smart contracts provide shared state, automated rules, and tamper-evident history. Around it all, ops, security, and governance define how identities, keys, monitoring, policy, and change control work across every participating organization and Oracle. To close, blockchain-based trust should extend what you already have, not replace it. Treat the ledger as a shared integrity layer and connect via APIs, so ERPs and core systems stay intact. Assume external data is adversarial and design strong Oracle patterns, reconciliation, and dispute paths. And operationalize everything by wiring the network into SOC, SIEM, and DevSecOps, so security, monitoring, and change control are first class.